All right, the final section, number 16 and following. So number 16 has to do with finding the area of a surface that is parameterized by U and V. All right, so the parameterization is given here. U goes from 0 to 2 pi, V goes from 1 to 4. You are asked to sketch and identify the surface and then to find the area of this surface using the given parameterization. All right, so that would involve double integral. Let's remember where we're going first. The area was a double integral. I mean, this is the definition of the area of any surface. Okay, but to calculate this, you actually have to find RU cross R magnitude of it, because that is the adjusting factor that you have to have. And then you do dA, where A goes, A has to do with U and V, right? So you would have to enter these boundary, the bounds for the double integral as you proceed. But let's find RU and RV and the magnitude of its product, okay, cross product. Oh, by the way, should I draw this first? Yeah, you're supposed to sketch this, so maybe you should sketch this first. All right, so the thing you should notice here is this is X, right? And this is Y. Y is independent. B does not appear in X or Z. So this is independent. Y is independently going from 1 to 4. But X squared plus Z squared is 4 cosine square U plus 4 sine square U, which is actually 4, right? And so that will give you a what? Well, if Y is 0, this will give you a circle of radius 2, like this, right? And then just go ahead and draw this thing here because Y is independent. And so this right now, all you have here is a infinitely long circular cylinder. But remember, V is Y, and Y goes from 1 to 4, right? So here, you just go from 1 to 4. And so now, this is the finite circular cylinder, and that's the surface area. We're looking for the surface area of this cylinder of length 3 that we're looking for, right? Okay, so that done, let's go ahead and find RU cross RV. RU is -2 sine U, 0 to cosine U. RV is 0, 1, 0. Notice here, I always do it this way, RU right above RV, because that way I can easily calculate by visualizing this. I can always calculate crossing and so on. I can easily calculate the cross product. The first component of the cross product is 0 minus cosine U. The second one, 0 minus 0. Last one, negative sine U minus 0. So that is that. And so this tells you, well, that the magnitude of this is the square root of, you don't even have to write this. It's 4 cosine square U plus 4 sine square U. It's actually the square root of 4, otherwise known as 2, right? And so that's the only integrand you have. So what is the area? Area of this circle. Let's see, I'm going to do which one? dV du. So U goes from 0 to 2 pi, V goes from 1 to 4 of 2 dV du. This double integral, when solved, evaluated, will give you the area of that cylinder. Cylinder of length 3. That's the identification of the surface. Remember, the problem says sketch and identify. So I should sketch this and identify this as a cylinder, a finite cylinder of length 3. Minus 1, that's 6. So 6 times the integral from 0 to 2 pi of du, that's 12 pi, and that is the surface area. Now, of course, you could have gotten this by looking at this, right? I mean, the circumference of this thing of radius 2 is 4 pi, okay? And then length is 3. So you can just this is 4 pi, this is 3. Of course, the area is 12 pi. And so you could have known this without the double integral, but the question asks you to do that using this parameterization. So you had to go ahead and do this. That was number 16, right? So next one should be number 17. And number 17 has to do with a flux. So let's draw the picture first. All right, number 17 has to do with finding the flux of F. F is given a three-dimensional vector field, and over this S, which is a part of this over a given square region R. Okay, so while it's not necessary for you to technically sketch this, it may help you to just sort of visualize what's happening. So let me go ahead and do that. And if you want to ignore this part, that's fine. But I think it's going to give you some insight into what you're about to do. All right. So this surface S is given as 4x plus 2y plus z is 12. Can you identify this? I hope you can see that this is a plane. Okay. Plane whose normal vector is 4, 2, 1, right? I mean, you can just read off your coefficients here. You can also easily graph this one because if x and, well, let's say if y and z are 0, then you have 4x is equal to 12. That's 3, right? And that's your x-intercept. If x and z are 0, you have 2y is 12. So that means 6. Y is equal to 6 is the intercept on the y coordinates. And then if x and y are 0, z is 12, so it's way up here. Okay, and you can connect these points. And that's going to give you sort of a part of this plane in the quadrant or octant 1, right? And this is really what you should just be able to visualize. Now, you are not trying to find these flux of F over this entire, triangular thing S, because it's above this region R. What does it say? The portion of this plane over the square region R, which is a 1 by 1 square. So you can just kind of draw this. Maybe I should do this in a lighter color and using lines here. Here's the line. It's going up here like this, up here like that. And 1, 1. So I don't know what the point is, but it's probably going to be something like this. Right? So the square S, sorry, the surface S is actually this part, which I will highlight. Well, let's see, a little bit of color here. This is the area, the portion of S, the portion of the plane that we are trying to find the flux through, right? So again, this part is not necessary for you to do this problem, but it may help you understand what you're doing. Okay, so how do you find the flux? What do you need to know? Okay, well, the flux is by definition F dot N. This is something that is perpendicular to the surface, ds. That's what you need to do. But remember, in chapter 6, we worked hard to show that this is actually equal to. Now, remember, this is a unit principal normal vector. You don't actually have to find that. You can do this parameterization RU, RV, take the cross product, and that with these bounds, okay, well, the du and dv or dv, du, whatever. So you take the dot product of F with the cross product of Ru and Rv, and this part is going to replace this thing. Okay, we don't have R, U, comma V. So how do you do that? Well, you have to parameterize the surface S and the portion of the surface above that region square 1 by 1 square. Okay, what do you do? Well, in case like this where Z can be written as an equation of x and y, right? So this is negative 4x minus 2y plus 12. That's the Z function. You can write this as f of xy. So you can just let u be x, v be y. This is one of the simplest ways to parameterize a surface when the surface is a plane, which is not vertical. Right? Function z is a function of x and y. Let x be u and y be v, and you will get a parameterization easily. All right, so z is -4u minus 2v plus 12. Remember, everything has to be written in terms of u and v, right? And so ru is 1, 0, -4. Rv is 0, 1, -2. Ru cross Rv is 4. And then remember, negative times -2 minus 0, so it's 2. And then 1 minus 0. Now, you got this vector, which is not surprising. That's obvious, okay? Because we just found this vector that comes out like this, okay? That's the same as not the principal normal vector, but this is exactly what you had here, okay? That's already in the equation. So, and that's what that is, okay? That's what the cross product is. The cross product is always perpendicular to the surface at the tangential point. But in this case, it's everywhere the same because S is a part of the plane. All right. And you know that U has to go from 0 to 1. V goes from 0 to 1. Okay, so that's pretty simple. All right, now let's do the flux then. The flux, oh, wait, I have to have F. According to the problem, F is y negative x 0. So y is what we now call v. Negative x is what we call negative u, and 0, right? And so if you take the dot product, which we will have to integrate, it's 4v minus 2u, okay, it's 4v minus 2u plus 1 times 0, which is, of course, 0. That's what we have to integrate. All right, so the flux, now, final stage, u goes from 0 to 1, v goes from 0 to 1. For v minus 2u, remember, this is what you have to integrate. And it doesn't matter if you do u dv du or du dv here, because both have the same bounds. But if you choose dv du, this is what you get. 2v squared minus 2uv, v goes from 0 to 1. So that's 2 minus 2u du, and that's 2u minus u squared going from 0 to 1. You get 2 minus 1, 2 times 1 times minus 1 squared, and that's just 1. And that is the flux of F through the surface, or the portion of the surface S over the square region. Okay, so that's number 17. Let's go to number 18. All right, number 18, you are given the surface, which is x is equal to 0. That means it's on the plane x is equal to 0. Y squared plus z squared is less than or equal to 9. All right, so just by casually looking at this, this has to be on this wall where x is equal to 0. And y squared plus z squared, if that sum is equal to 9, then of course that's a circle of radius 3, right? And it's less than. So you're talking about everything inside of this circle. So this is a solid circle that's on the plane x is equal to 0. The problem actually tells you that it is the vertical disk of radius 3. Now, disk means the circle and everything inside. Circle is only the circumference, right? So we're talking about the solid disk on the YZ plane, and C is the boundary of this. All right, we are also given a three-dimensional vector field, which is x minus z, y. We are to use the Stokes theorem to find the double integral of the curl of f dot n ds. So this is the flux of the curl of F over this solid S, which is the disk, right? So we have to find this. But of course, the theorem, what does Stokes' theorem say? Stokes tells you this is equal to the work done by F along the boundary. Okay, so again, the double integral is equal to the single integral, just like in Green's theorem. All right, so this is what you have to find. Now, you have to find this, but using Stokes' theorem, you don't actually have to find the curl of F or parameterize this disk S. What you do have to do is to parameterize C, right? So R of T. Now here, X is 0, and Y and Z have this relationship. So this is 3 cosine T, 3 sine T. T goes from 0 to 2 pi. That's going to give you the complete circle, the boundary of, of the disk S. And so that is the good parameterization of the boundary circle C. What else do you need? Well, this is R prime dt, right? So I have to have R prime. So that's 0, negative 3 sine t cosine, 3 cosine t. All right, F is x, negative z, y. X is 0. Negative z is, well, let's see. This is z, so negative 3 sine of t. And then y is, of course, 3 cosine of t. All right, we are to find the dot product, right? Because that's f dot r prime dt. So you take the dot product of these two, you get 0 plus 9 sine squared t plus 9 cosine squared t, which is simply 9. How wonderful, right? And that's because the problem has been carefully designed to avoid messy calculations. All right, so what are you supposed to find? So the double integral that we are asked to find is just a simple integral from 0 to 2 pi of 9, right? That's f dot r prime dt. And that's simply 18 pi. And that's simple. Now, you may want to look at the answer key, because I have inserted an extra thing. If you want to verify Stokes' theorem, you can actually directly calculate this if you are willing to parameterize S using U and V. Okay, so for details, you can look at the answer key where I supply the other part, or the this side, and to show that that's also 18 pi. Now, you didn't have to do that, because in number 18, it says just use Stokes' theorem to find it, right? But if you're interested in directly finding the opposite side of Stokes' theorem, and to show that that side is also 18 pi, then you can do so. Just check the answer key. All right, if I remember, number 19 is the last question on this thing. So let's go ahead and do that. It has to do with divergence theorem. A three-dimensional vector field is given, and that's 2x. Hold on a second. Number 19, use the divergence theorem to find the flux of this vector. Oops, that's it's 2x, a vector field, over the surface, which is the 6 sides of the 1 by 1 by 1 cube, the unit cube E described here. X, Y, and Z both go from 0 to 1, all go from 0 to 1. Okay, so how much of the stuff is leaking coming out of this square or the cube when F, the vector field, is described this way, right? If you know the divergence theorem, you find that this is a really easy question. If you don't know the divergence theorem, then it's probably impossible to do. Because the opposite side, the other side of the divergence theorem would require you to calculate the surface, the flux over each of the 6 sides, and that's going to be much more time consuming. Well, you know that the flux, which is defined as, if the surface, the bounds, which consists of 6 rectangles, sorry, the 6 squares is the surface S. The flux is defined as, F dotted with a norm, the principal normal vector. This is what you have to do. But by divergence theorem, it's the same as the triple integral over this entire solid of the divergence of F. Okay, but what is the divergence of F? Well, the divergence of F is the partial of this with respect to X. Oops, that's not a vector, right? Plus the partial of this with respect to Y, plus the partial of this with respect to Z. So that's just 2. Okay. And so this is all you have to do for this problem here. And again, it doesn't matter if you use dz, dy, dx, or any of its 5 other permutations. You get 2 times the volume of E, which is 1 by 1 by 1. That's 2. And that is the simple answer for number 19. Okay, so I have finished all that. And now it is time for you to review your entire semester, but focusing on what I think is important. Those are the things that I listed on the first part of that, the checklist for the final exam. So along with the answers to the checklist and the answer key for these 19 questions, you should now be ready for your final exam. All right, have a wonderful day, evening, whatever that is, and I will see you at the final. Thank you so much. I really appreciate your hard work and discipline.